Today we'll see how to define vector space from given other vector space, maybe given same vector space. Recall that we have a field and then the set V with two operations, addition and S multiplication on K is called a vector space when it satisfies vector space axioms. The question is, how can we define another vector field from this vector field? Because this is a set, we can have some set operation such as union, intersection, or subset, thingy. So first, you might think about union, intersection, subset, but we will start with a subset. It is one reason is that it is the basic operation. The other is that let us think you have two u and let us think u plus u and s multiplication on u and w and plus in w and w. Then you can have some u intersection w and plus intersection u union union w and something heart u union w. The problem is that what is this guy? You cannot define easily what is, let's say, u in u and v in w. Of course, these two guys are u union w, but what is u plus? I just do not write here for simplicity. Let us write just plus and heart. This is defined on u and v, union. So I mean plus is the u union w times u union w. So it is binary operator in u union w. Then you can say what is u plus w. Can you say it from tu? No, because it is not defined for adding v. Plus in w? No, it is not defined in how to add u. So you cannot say this thing. So these guys are not well defined. So you cannot say something about union. Similar thing happened to the intersection. Then what we can do? We can do is subset. So let us assume u is a subset of v. This is just a subset. Then we can use what is this. We want this should be also K vector space. Then question is when this is K vector space, because plus is what we define plus is, in fact, plus is defined on V and heart is defined on V. But so, and this heart and plus satisfies all the vector space axiom in V. Then what we want here is that this guy and this guy, if we want to say this is vector space, we want this becomes this way, this becomes, oh, sorry, I should write this K. Oh, not you. So this should be this. So and this should be this. So we know this. We know. Then we want these guys. So if we write U for distinction, question is, first, can we define this from this? We can define this to this just simply because plus and heart is U is a subset of V. We can just assume this operation is the same value when U. So for how to relate to this, we can just define this for U in U1, U2 in U. U1 plus U2 equals U1 plus, but in U, U2. So if this is true, then we can define this plus U uniquely without any extra assumption. There is no ambiguity because we know this is true. We know this value, then this value is uniquely defined by the above operation. Similar thing happens A in K and U in U. We can say also A times U is A heart U, U. I should write small u. A heart U, U. This should be U. Yeah. Also, left one is unique. So left one is well defined and unique because U is a subset of V. So left one is well defined. Then right one is well defined because left one is exactly the same with the right one. So then this is true. So now we don't need to distinguish them, so we will use same notation, just plus and heart. So we don't need to check associative or distributive because if it holds above, it should hold below. Then what can be different? First one, it is commutative, but it cannot be closed. It means that what happens, U plus V. So question is, U1 is in U, U2, U1 and U2 are in U. Then U1 plus U2 is in U. It can be true, but it cannot be true. It depends on how you define U. So you should find U satisfying this property. This is closure relation. Similarly, A in K and U in U, A heart U should be also in U. These two conditions are needed. This is how you define closure. And also, one of the important things is that you need a zero and identity should be. And for every element, there is just minus U also in U. So this might change how you're defining the U. So you should find the U which satisfies these things. So if this is satisfies, for you have given V plus heart, it is K vector space. You have U plus is same with above, heart same with above, but restricted only in closed in U. Also K vector space. And it is subset. In this case, this is called subspace. of K of V. So subspace is nothing, just you have vector space. Then if each subset with the same operation, important thing is that I want to emphasize is that with the same operation is also a vector space, it is subspace. And yeah, and with this you can now define intersection and union. Let us go first intersection. You have V heart is a K vector space. You cannot define random intersection as I told in the beginning, but you have U1, sorry, I want to pick U1 plus heart is a subspace of V. And similarly, U2 plus heart is a subspace of V. In this case, you can say U1 union U2 and plus and heart without any confusion, because in this case, this plus is defined on V and U intersection V, intersection U2 is subset of V. So every element of U1 intersection U2, you can find each result of summation, each result of addition, and each result of multiplication. You can always find it. And because they are vector space, what you have to check is that closure so for all U1 and U2 in U1 intersection U2, U1 plus U2 is intersection in the U1 intersection U2. It's simple. For you have only plus in U1 and plus in U2, also plus in V. You know, for U1, U2 in U1, if the above is true, then U1 is U1 in U1 and U2 is in U1. Then because it is subspace, U1 plus U2 is in U1. Similar thing happen with U2. Then summation is in U2. Because U1 is in U2, U1 plus U2 is U1, then we can say U1 plus U2 is in U1 and U1 plus U2 is in U2. There is, it is equivalent to U1 plus U2 is in U1 intersection U2. So if we assume this is true. So you check closure is closure on addition, and similar thing you can check is that S multiplication also you can do the same. The story is same. It is in U1, it is in U2, so it should be in U1 intersection U2, so it is closed. And also 0 is in U1, 0 is in U2, so 0 is in U1 intersection U2. And for any choice of U1 or U2, U1 in both U1 intersection U2, there is minus U1 plus minus U is intersection of U1 and U2. So everything is okay. So this is clearly vector space. In other words, V plus heart is a K vector space. Let me summarize. Then and u1, u2 is plus heart is a subspace of V. Subspace of V. Then u1 intersection u2 and same plus and same S multiplication is also vector K vector space, and u1 intersection u2 is subset of V. Also, this is subspace of V. So for the subspaces, I want to emphasize, for the subspaces, their intersection is also vector space. That is what you usually call. So now you know how to find second way. First, you find from vector space, you know how to find subspace. And second, if you have two subspace of vector space, then you can find that their intersection is also a subspace. So it is vector space. Then third thing you want to do is that, then how about union? Because I don't want to write same thing again, let me use V is this thing is also true. Maybe I can copy and paste. Let me copy. I noticed that I don't know how to paste. It's not working. Okay, let me just skip. Okay, I don't know how to paste, so I just use same notation. So V is a vector K vector space, and U1 and U2 are subspace. The question is then U1 union U2 and plus and heart. Can you ask this is K vector space? If it is true, it is also subspace. But if it is not a subspace. It is very simple. You can choose any U1 in U1 and U2 in U2. Then U1 plus U2 and also okay, this does not say something. For simplicity, assume U1 intersection U2 is 0. Vacuum, empty set. Okay. Then again, U1, let us assume U1 in U1, U2 in U2. Then U1 plus U2 is not in U1 and it's not in U2 because U1 plus U2, U1 is closed only in U1, U2 is closed in U2. This should not be in U1 or U2. It means, but U1 is in U1, U1 is, it means U1 is of course U1 union U2. U2 is in U1 union U2, but U1 plus U2 is not in union of U1 and U2. So this means that this K vector space? No, this is not vector space. So interestingly, intersection is a vector space, but union of subspace is not a vector space in general.